My name is Bill Henry. I'm going to explain how to optimize the chiller and chiller plant, including my method of measurement and performance verification. As a young engineer, I began my career in the energy transformation business. In those days, it involved the production and use of steam, including high-pressure boilers, large piping distribution systems, and energy-intensive processes. Later on, coming to California, I became heavily involved with large cooling systems, including chillers and chiller plant operation. As a consulting engineer, I designed, installed, and supported these chiller plants. I'm a professional engineer in California and New York and hold 2 U.S. patents pertaining to chiller plant operations. I view the chiller plant as one of the 3 elements of a chilled water system. Those 3 elements are users, like the environmental cooling systems, process cooling, or equipment cooling. Then there is the chilled water distribution system that includes piping and attendant pumps. Finally, we have the production of chilled water by the chiller plant. Production being the operation of the chillers, condenser water pumps, and cooling towers. By limiting our focus here to production elements, we can establish an intelligent boundary for measurement and analysis of energy demand and create consistent metrics for any facility. Of the various strategies for optimizing a chiller, the biggest bang for your buck is achieved by implementing condenser water reset. For instance, Siemens demand flow pumping, while it includes an expensive control scheme for the entire chilled water system, careful analysis shows that it depends on condenser water reset of the chiller for the majority of achieved saving. This goes for the Johnson Controls optimum energy method as well. When implementing an optimizing strategy, you should want to verify savings and preferably do it on a real-time basis. So does the cost of installation pay off? And you need to ensure that the control system is not corrupted and won't damage the chiller. So I developed a model to provide tools for control sequencing and real-time measurement and verification, but we'll get to that later. So let's look at the basic parameters we need to know to implement condenser water reset to improve chiller efficiency. This chart provides a conservative condenser water temperature for any operating load expressed here as a percentage of the chiller's rated full load. The condenser water temperature is plotted on the y-axis and the load is plotted on the x-axis. The chart provides a generic formula to automatically determine the condenser water set point for any load. Now, the conservative data points shown on the chart come from Standard 550 of the Air Conditioning, Heating, and Refrigeration Institute, and I'll refer to this as the AHRI profile. You probably recognize these data points as the ones used by manufacturers to provide the required IPLV, or part load efficiencies, as required by code. So these operating points are acceptable for any chiller that is guaranteed to meet these code requirements. I want to note that the leaving chilled water temperature for this criteria is 44 degrees Fahrenheit. And a bit later, I'll show you the conservative nature of this profile. For now, in the next slide, I will simplify the curve. In the first chart, we can reduce the curve to a straight line by fixing the lower limit of condenser water temperature at 50% load. But we can also introduce a single point step down of the condenser water temperature as shown on the second chart. While this does not provide as much savings, it can be simply implemented and should satisfy those jurisdictions that require some reduction in compressor lift at part load. Now let's look at a specific chiller. Here are data sets for a specific non-generic 400-ton chiller with R123 refrigerant. The first table profiles the condenser water temperatures versus load at a 44 degree Fahrenheit leaving chilled water temperature. And the second table profiles the condenser water temperatures at a 50 degree Fahrenheit leaving chilled water temperature. The most efficient condenser water temperature is plotted for each load condition in 10% load increment. Now we can compare these operating profiles to the AHRI 550 profile described in the previous slides. This set of curves compare the AHRI 550 profile with the 400-ton chiller. The upper or blue curve represents the AHRI 550 profile, and the lower red curve represents the profile for the 400-ton chiller. In the first chart, the leaving chilled water temperature is 44 degrees Fahrenheit for both profiles, AHRI and the chiller. In the second chart, the leaving chilled water temperature is 50 degrees Fahrenheit for the chiller. Thus, the AHRI profile works in both situations. Just in case you are wondering, the upward lift of the red curve at the beginning or left side is due to the manufacturer's minimum refrigerant head pressure requirement, plus a safety factor. I have a couple of questions for your consideration. Are you currently using condenser water reset to optimize your chillers, or are you using some other optimizing method? If you wish, you can provide some feedback. Just send me an email to the address listed here. As shown, the AHRI profile for condenser water reset is a very conservative approach, but the typical chiller operation can see even greater performance gains if only the most efficient condenser water temperatures are known. So we need a method or tool to determine the lowest allowable condenser water temperature under any given set of conditions. Therefore, I developed a customizable modeling solution to solve this problem. This is a comprehensive and predictive model that will not only provide the most efficient condenser water temperatures, but also provide real-time metrics to help evaluate the performance of a specific chiller and chiller plant. When optimizing a chiller, we need to recognize a few issues that may create problems. Measuring the actual load accurately can be difficult due to the configuration of piping and pumps of the chilled water distribution loop. You also need responsive and reliable temperature sensors. I have actually found that it is much easier to measure the flow in the condenser water loop and prefer to optimize the condenser water based on heat rejection, but it can be done either way. Now there is the possibility of allowing the condenser water temperature to fall below the curve, thus degrading chiller performance and or limiting its capacity. The worst case scenario would be to damage the compressor, but one would really have to try hard and implement a very aggressive or low condenser water reset regime. Verifying results can be problematic, and so verifiable metrics to evaluate performance are important. One method is to compare current operation with last year's operation, but that is time-consuming and can be unreliable. My solution was to develop a model of the chiller using actual operating conditions and predicting the performance in a verifiable manner. ASHRAE provides instructions and methods for collecting data that can be used for historical analysis of operation and its efficiency. A model must be customizable to match any specific chiller and its operating conditions. But with a good model, one can make real-time predictions. These predicted results become a metric that can be compared to actual operating power demand. The same model can predict operation with different scenarios. For instance, operating at a lowered condenser water temperature versus the design condenser water temperature. By predicting a power demand that can be compared to the actual demand, one has a verifiable tool, and a model can be evaluated with coincident operating conditions, thus providing real-time results. 6 pages of the 40-page ASHRAE Guideline 22. This is quite a document. It describes multiple points of measurement and gives details on instrumentation and calculation methods. The result is a lot of tabulated data that will require much time and effort to analyze and generate a meaningful report. I wonder if anyone has ever gone to the trouble, outside of a few researchers. This is an example of how a prediction model can display real-time results coincident with a display of monitored readings. The real-time monitoring display on the left shows the operating condenser water temperature to be 71 degrees Fahrenheit, and the actual power demand at the chiller is 130 kilowatts. On the right, the real-time prediction display predicts a power demand of only 124.7 kilowatts for the chiller. Most likely, the chiller barrels are dirty and need to be cleaned. The real-time prediction display also predicts what the chiller power demand would be if the condenser water temperature was the design temperature of 85 degrees Fahrenheit. A simple calculation will show that this optimized chiller, which is 82% loaded, is saving 45.8 kilowatts. So, we have a diagnostic metric and a metric to evaluate performance. What is a chiller model? It is a tool used to predict results. That is, a mathematical tool for modeling energy demand. Engineers use models to predict energy demand for new building designs. Chiller manufacturers use models to select the proper chiller for a given project and to support their sales efforts. The numbers provided by your friendly representative are generated by some modeling program. DOE, or Department of Energy, has a model that is used in building simulation programs like eQuest and Energy Plus. It can be used by consultants to support energy rebates handed out by PG&E or your local electrical utility. Simulation tools like eQuest and Energy Plus provide fixed results for one-time use based on generic chillers. Any good model can be programmed to match a specific chiller to provide optimal condenser water temperatures at various loads and to develop a condenser water control algorithm for that chiller. On the other hand, a real-time model uses real-time inputs like load and water temperatures and runs the model in a PLC or other device coincident with the chiller's operation. Since it is nearly impossible to repeat a given load and weather conditions, this makes real-time prediction a valuable concept. In the next slide, I'll show examples of a couple different models. The first model on the left is for York chillers. I found it buried in the York Count program. It consists of a polynomial equation with 8 terms. There are 2 variables, where x is the condenser water temperature in degrees Fahrenheit and y is the load in percent. 2 sets of 8 constants, one for variable speed operation and one for constant speed. The resultant P is power demand as a function of maximum demand, where 1 equates to the maximum demand. The second model comes from the Department of Energy and the one alluded to in the previous slide. It consists of 5 rather complicated equations. There are books written to describe how to use this DOE tool. One source, the HVA Simulation Guidebook, is referenced on this slide. While these models work well for generic chillers, they are not so handy when applying to specific chillers with alternate conditions. My process-based chiller model provides a set of manageable equations for programming and control. The first equation provides the optimized entering condenser water temperature for a given chiller based on load. The next equation is the relationship between rejected heat and actual load and can be used to program condenser water control based on rejected heat. Efficiency curves can then be derived from data published by the manufacturer for a given chiller. Therefore, power demand is a function of load and efficiency at temperature. This process model provides relatively simple equations that can be readily programmed into an off-the-shelf PLC. Therefore, it is ideal for retrofit situations and not limited to proprietary control systems. The model formulas can be customized to match any specific chiller using the published chiller specifications by the manufacturer. This is accomplished with a software model. The software model can also be used for research and testing by reprogramming additional parameters for the more rigorous applications. The next slide describes the software model in a spreadsheet format. The formulas, 2 slides back, were developed using the spreadsheet model shown here. All of the required inputs, primary calculations, and iteration macros are expressed in this worksheet. Material properties and supporting data located on other worksheets are accessed directly by spreadsheet functions. Calculations are based on thermophysical properties, flow dynamics, and system losses. The calculations include my unique patented method to characterize and implement refrigeration mass flow limits. This customized chiller model can be evaluated with various combinations of condenser water temperatures, chilled water temperatures, and load. This slide is a repetition of my notes on the last slide. The video presentation can be paused at this point for readers. The chiller is the linchpin when it comes to optimizing the chiller plant, but that is only half of the equation. Significant additional improvements are achieved by balancing the cooling tower operation with the chiller to maximize energy efficiency. Additionally, variable flow condenser water can offer additional savings, especially where multiple pumps are configured in parallel with high pressure loss piping systems. By the way, speaking of variable flow, if you run across the Siemens demand flow pumping concept and study the method as exposed by their patents, most of the savings is still due to the chiller operating with lowered condenser water temperatures. I might mention here that the concept for variable flow condenser water has already been exposed by a patent that predates the Siemens patent by several years. Let's now take a closer look at cooling towers. The objective when optimizing a chiller plant is to have the lowest overall average energy use over time, but just controlling to the lowest, most efficient condenser water temperature for best chiller efficiency can cause a cooling tower to overuse energy for a significant portion of the time. Up to half of the efficiency gains with the chiller can be lost by poor cooling tower operation. The cooling tower cannot achieve the desired condenser water temperature due to high wet bulb conditions and therefore operates at full speed. Carrier and Johnson Controls solve the problem with methods using complicated computer routines that test and adjust condenser water temperature, then test again in an effort to achieve the lowest common temperature for best power demand. Another theory promotes the use of wet bulb boundaries, but results are limited. Here is a simple solution I can show you. That is, limit cooling tower capacity based on load so the fan power matches the rejected heat load. Consider this a thought experiment. We have a typical cooling tower with condenser water temperature control that regulates fan speed and condenser water reset. Imagine switching to a smaller tower, say half capacity, when the load is at 50%, and say the condenser water set point is below the wet bulb condition. Even if the smaller tower fan speed maxes out, the power demand is limited. Condenser water set point is not met, but the condenser water temperature is still within the chiller's maximum limit. Now, instead of actually switching to the smaller tower, implement a capacity limit control in addition to the variable set point control. When the load is less than full, a fan speed control limit is implemented on top of the condenser water set point. This can be done quite easily with a smart algorithm that uses the same inputs required for condenser water reset and control. For measurement and verification of the cooling tower, we can choose a simple rule of thumb model, such as the one used by YorkCalc, or a more complicated time-consuming model. The Department of Energy has their cooling tower model, but there is a potentially simpler model that is publicly available. This is the Venkatesh model, shown here on the right. It is a polynomial equation with 35 terms. Still, when I ran this one on my desktop, it took about 24 hours to complete. The rule of thumb model, shown on the left, works quite well for the operation of the cooling tower at the design condenser water temperature, and it can then be used to compare with real-time results of the cooling tower power demand. For example, the rule states that a 400-ton cooling tower with a 30 horsepower motor has a power demand of 0.075 horsepower per ton of load. So let's complete the discussion I started in slide 15 and include the cooling tower operation. The real-time prediction for cooling tower power demand at the given load and the 85-degree design condenser water temperature is 19.7 kilowatts, but the actual measured demand is 24 kilowatts. So the cooling tower is using more energy to provide a condenser water temperature of 71 degrees. When we combine the chiller and cooling tower operating demand, the total is 154 kilowatts with the 71-degree condenser water. This then can be compared with a plant operating at the design condenser water temperature of 85 degrees, with all other conditions being equal, and we see the combined power demand is predicted to be 190.2 kilowatts. Therefore, the predicted savings for the chiller plant is just 41.5 kilowatts versus the 45.8 kilowatt savings of the chiller. So now we have a more realistic evaluation of the actual operating savings, and it is done in real time. I just want to reiterate that the chiller is 80% loaded in this example, and also the cooling tower operations in combination with the chiller and the different possible wet bulb conditions, plus plant loads, would require a separate presentation to cover all the potential, actual, and predicted scenarios. So I'll wrap up without going there. Here are my patents regarding chiller plant operations. The first one expires in a couple of years, and the second one was just granted in December of 2018. So if you really want to dig into the details, have at it. If you have questions later on concerning this presentation or my patents, you can contact me at the following email address. Send me an email for best response. I tend to procrastinate when it comes to checking my voicemail. Thanks for listening.